Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 11. We are concluding our discussion of Newton's second law of motion, force and acceleration. Let's revisit our big idea. An object accelerates when a net force acts on it. We will be covering 3 learning objectives, the last 3 in this unit. Distinguish between force and pressure. Explain why the acceleration of an object in free fall does not depend upon the mass of the object. And the last one, cite and discuss the factors which affect the air resistance force on an object. Again, learning objective number 7, distinguish between force and pressure. If you think about the air you breathe, a gas, and the water you drink, a liquid, you'll realize they have some things in common. Both air and water flow and have indefinite shapes. Unlike concrete, which is a solid, because of their common characteristics, gases and liquids are also called fluids. Properties of fluids. How does a fluid differ from a solid? Suppose you put an ice cube in a glass. The ice cube has a certain mass and shape. Neither of these quantities depends on the size or the shape of the glass. What happens, however, when the ice melts? Its mass remains the same, but its shape changes. The water flows to take the shape of its container and forms a definite upper surface. If you boiled the water, it would change into a gas, water vapor, and it would also flow and expand to fill whatever container it was in. But the water vapor would not have a definite shape. Both liquids and gases are fluids. Fluids are materials that flow and have no definite shape of their own. Can Newton's laws of motion and laws of conservation of momentum and energy be applied to fluids? In most cases, the answer is yes. But in some cases, the mathematics is so complicated that even the most advanced computers can't reach definite solutions. By studying the concept of pressure, you can learn more about the motion of fluids. Applying force to a surface is pressure. Pressure, which can be represented by the equation P equals F over A, is the force on which surface is divided by the area of the surface. F represents the force on the surface, and is assumed to be perpendicular to the surface area A. No matter how you place a book on a table, the force of the book on the table is the same. You can check this by placing a book in any position on a bathroom scale. You'll read the same weight in all cases. Place a book in different positions on the palm of your hand. Although the force is always the same, you'll notice differences in the way the book presses against your palm. These differences, again, are due to differences in the area of contact for each case. For a constant force, an increase in the area of contact will result in a decrease in the pressure. The amount of force per unit of area is called pressure. Again, more precisely when the force is perpendicular to that surface area. So you can see that we can apply it to fluids and we can also apply it to solids. Force is measured in newtons. It's different from pressure. The pressure is measured in newtons per square meter, or also called pascals, large P, little a. 1 newton per square meter is equal to 1 pascal. You can exert more pressure against the ground when you stand on one foot than when you stand on both feet. This is due to the decreased area of contact. Stand on one toe like a ballerina and the pressure is huge. The smaller the area supporting a given force, the greater the pressure on that surface. You can calculate the pressure you exert on the ground when you are standing. One way is to moisten the bottom of your foot with water and step on a clean sheet of graph paper. Count the number of squares on the graph paper contained within your footprint. Divide your weight by this area and you have the average pressure you exert on the ground when standing on one foot. How will this pressure compare with the pressure you exert when you stand on 2 feet? Take this for example. The author of one of the books that I'm reading applies appreciable force when he breaks a concrete block with a sledgehammer. Yet his friend, who's also an author of the book, is sandwiched between 2 beds of sharp nails and is unharmed. The friend is unharmed because much of the force distributed over the more than 200 nails that make contact with his body. The combined surface area of this many nails results in a tolerable pressure that does not puncture the skin. So, how does the area of contact affect the pressure a force exerts on an object? Our next learning target is explain why the acceleration of an object in free fall does not depend upon the mass of an object. Recall that free fall occurs when a falling object encounters no air resistance. Also recall that Galileo showed that falling objects accelerate equally, regardless of their masses. This is strictly true if air resistance is negligible, that is, if the objects are in free fall. It is approximately true when air pressure is very small compared to the mass of the falling object. For example, a 10 kilogram cannonball and a 1 kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. This experiment, said to be done by Galileo from the Leaning Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is a straightforward application of Newton's second law and is the topic of what we're going to talk about next. Recall that mass, a quantity of matter, and weight, force due to gravity, are proportional. A 2 kilogram bag of nails weighs twice as much as 1 kilogram bag of nails. So a 10 kilogram cannonball experiences 10 times as much gravitational weight as a 1 kilogram stone. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone, because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. In symbolic notation, force over mass, large F, which stands for force, is the weight acting on the cannonball, over small m, which stands for the correspondingly large mass of the cannonball. The small f and m stand for the smaller weight and the smaller mass of the stone. The ratio of weight to mass is the same for these or any objects. All free-falling objects undergo the same acceleration at the same place on Earth. Our last learning objective is cite and discuss the factors which affect the air resistance force on an object. A feather and a coin fall with equal accelerations in a vacuum, but fall unequally in the presence of air. When falling in air, the coin falls quickly while the feather flutters to the ground. The force due to air resistance diminishes the net force acting on the falling objects. Speed and area. The force due to air resistance is experienced when you stick your hand out of the window of a moving car. If the car moves faster, the force on your hand increases, indicating that air resistance force depends on your speed. If you, instead of just your hand, you hold your physics books out the window, I don't suggest this, with the large side facing forward, exposing maximum frontal area for the book, the air resistance force is much larger than it was on your hand at the same speed. You find that the force of the air resistance is also proportional to the frontal area of the moving object. Hence, the air resistance force an object experiences depends on the object's speed and area. An expression describes a relationship between speed, area, and air resistance. The air resistance force is proportional to speed times frontal area. The expression shows that the air resistance force is directly proportional to the speed in the frontal area of the object. Terminal speed. When the air resistance force on a falling object, like skydivers, builds up to the point where it equals the weight of the object, then the net force on the object is zero and the object stops accelerating. We say that the object has reached its terminal speed. Terminal speed is the speed at which the acceleration of a falling object is zero because friction balances the weight. If we're concerned with direction, which is down for falling objects, we say it's reached its terminal velocity. Terminal velocity is terminal speed together with the direction of motion. A falling feather reaches its terminal speed quite quickly. Its air is large relative to its very small weight. Even at small speeds, the air resistance has a large effect on the feather's motion. A coin, however, has relatively small area compared to its weight, so the coin will have to fall faster than a feather to reach its terminal speed. The terminal speed for a skydiver varies from about 150 to 200 kilometers per hour, depending on the weight and orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through air. Body orientation also makes a difference. More air is encountered when the body is spread out and the surface area is increased, like that of a flying squirrel. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavier person spreads out like a flying squirrel while the light person falls head or feet first. A parachute greatly increases air resistance and cuts the terminal speed down to 15 to 25 kilometers per hour, slow enough for a safe landing. If you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of a building, you'll notice the heavier baseball strikes the ground first. This is due to the buildup of air resistance at higher speeds. At slow speeds, air resistance is often negligible, but at high speeds it can make quite a difference. The effect of air resistance is more pronounced on the lighter tennis ball than on the heavier baseball, so the acceleration of the fall is less for the tennis ball. The tennis ball behaves more like a parachute than the baseball does. When Galileo reportedly dropped the objects of different weights from the Leaning Tower of Pisa, the heavier object did get to the ground first. However, the time difference was only a split second, rather than the pronounced time difference expected by the followers of Aristotle. The behavior of falling objects was never really understood until Newton announced his second law of motion. Isaac Newton truly changed our way of seeing the world by showing how concepts connect to one another. The connection between acceleration, force, and mass discovered by Newton in the 1600s led to men landing on the moon in the 1900s. Newton's second law was primarily responsible for this feat. Question to think about: what factors determine the air resistance force on an object? Thank you.